All right, so we're going to talk about the binomial theorem. So 8.5, binomial theorem. What I want you to do is I want you to look at these binomial expansions. So we're going to look at x plus y to the power of 0, and then x plus y to the power of 1, x plus y to the power of 2, and then last but not least, x plus y to the power of 3. All right, so take a moment and I want you to expand these binomials. So pause the video, expand them, and see if you get what I get. Okay, so let's look at the first one. Anything to the power of 0 is going to be 1. So that means we just have 1. We raise x plus y to the power of 1. That means we're just writing out the binomial once. So this is just x plus y. For x plus y squared, so hopefully the first thing you did was you wrote out x plus y twice. So that is going to give you x squared plus 2xy plus y squared. And then finally, the third one, you'd have written this binomial out 3 times. And so x plus y times x plus y, which we already know is this. So we all had to do was multiply that trinomial out again, and we would have gotten x cubed plus 3x squared y plus 3xy squared plus y squared. So now I want you to think of some patterns. What do you notice about the original problems in black and our answers in blue? So 1, the x plus y, the x squared plus 2xy plus y squared, and then the x cubed. And does it work for all of them? So take a moment, think about it, you might jot it down, and then I will we'll walk through it. All right, so the first thing that you should have noticed is that in each expression, you actually have one more term than your exponent. So notice that one more term from 1 would be 2. Notice you have 2 terms. 1 more than 2 is 3. Notice you have 3 terms. 1 more than 3, you have 4 terms. So we're going to write that down. So in each expansion, there are n plus 1 terms, right? Where n is the original exponent. So that's the first thing that you should have noticed. Another thing that you should have noticed is that x and y have symmetric roles. All right, what does that mean? There's symmetry. So notice, and you might not be able to see it here, but later on in our expansion, especially here, notice that your x's go from 3 to 2 to 1 to none. And notice that your y's go from 0 to 1 to 2. Oh, that was supposed to be a 3. So that was my bad on that one. So go ahead and erase that in your notes right there. So they have symmetric. So powers of x decrease by 1 each time, and the powers of y increase by 1 each time. All right, and the last one you should notice also is this. If you add in each term, if you add your exponents together, not that we would because they're not the same they're not the same base, but if you add them, you actually get the original exponent. So notice that here we have a 2 and a 1. Here we have 1 and a 2. So if you add those together, it will add to the original exponent. So I'm running out of room right here, so I'm going to write that last one over here. And I'm going to write it in black. So the sum of the powers of each term is n. Okay? So, if you think about it, this multiplication wasn't too bad, right? Maybe multiplying it 3 times was a little bit of a pain, right? So we want an easier way. So there's something called Pascal's triangle. So Pascal's triangle. And it's used to remember, so used to remember the coefficients in binomial expansion. All right. So let's start Pascal's triangle. So let's see if you guys can find the pattern. So the first row has a 1. Right? The next row has a 1 and a 1. All right? The next row has a 1, 2, 1. See if you can pause the video and guess what the next row is going to be. The next row is going to be 1, 3, 3, 1. Okay, if you got that right, try to guess what the next row is going to be. The next row is going to be 1, 4, 6, 4, 1. And the next row is going to be a 1, 5, 10, 10, 5, 1. Right? So if you've guessed the pattern, right? Awesome. If you didn't guess the pattern, let's figure out what's happening. So I'll take this set of numbers right here. Right? So Right? What's happening is you are adding 6 plus 4 together, and it will give you the 10. So 4 plus 1 will give you the 5. 3 plus 3 will give you the 6. So technically this will be a 6, a 15, a 20, another 15, and another 6. Ones always start the pattern and end the pattern. Okay? And then you add the numbers to get to the next one. This is what we consider the 0th row. This would be the first row. This would be the second row, right? And so the 0th row, the first row, the second row, each row corresponds to the original exponent. So that means that the exponent was, say, 2. We would look at the second row. Okay? Now, you might forget that. So how can I know for sure? Well, here's a little hint. The second number actually corresponds to the exponent. All right? So if we look at the third row, notice the second number is a 3. So this is actually the third exponent. If you look back here, notice it was a coefficient of 3 right here. Right. Fun little fact. There's a lot of different things to remember about Pascal's triangle. Okay, a lot of different things. So like notice that these are always ones. Notice that here is 1, 2, 3, 4, 5. So this is a row of 6. Notice here I got 1, 3, and then 6, and then 10. So notice it's going plus 2, plus 3, plus 4. The next one's going to be plus 5. Okay, so there's different patterns happening here. Okay, the other thing that's happening, you can actually add the numbers up. So notice that 1 plus 2 gives you 3. 3 plus 1 gives you 4, right? And 4 can be written as 2 squared. 1 plus 3 is 4. 4 plus 3 is 7. 7 plus 1 gives you 8, which is really 2 cubed. 1 plus 4 is 5. 5 plus 6 is 11. And 11 plus 4 is 15. Plus 1 is 16. 16 is 2 to the power of 4. All right, so there's a lot of different little patterns happening in Pascal's triangle. If I had all the time in the world, I would sit here and show you all the different Pascal's triangles. You can actually use Pascal's triangle also to help you with powers of 11, right? 11 to the power of 0 is 1, 11 to the power of 1 is 11, 11 squared is 121, 11 cubed is actually 1331. Stuff like that. So there, again, what I suggest is Googling little things about Pascal's triangle.